Test, test, test. Okay, cool, cool, cool. We're back. We had some updates last night, so things look like they got a little sideways, unfortunately. Let me adjust levels a little bit here, because those don't look quite right either. Okay, are we good now? I think we're good now. Anyway. As I was saying, we are back for... Oh, that's spiking red. We don't want that. Okay, a little bit lower. Okay, cool, cool, cool. We are back with Advent of Code Day 14 of the 25-day annual Advent of Code coding challenge. Every December we have little joyous little puzzles for us to go through, and this year I'm doing them on stream so that I actually have motivation to keep up with it, right? Before I get into today's, I didn't quite finish yesterday's part 2. And as you can see from here, you can tell what I ended up doing. I ended up cheating, like a horrible, horrible cheater. I went through a few different implementations in Ruby, and I just could not find a version of the Chinese algorithm that would work for me. Chinese, what's the middle word for that? Chinese something theorem, right? I don't remember. It doesn't matter. I'm never going to use that again in my life, and it's out of my memory. Anyway, there's this really cool site, Wolfram Alpha, that can solve equations for you. So this is what I used. I took my input and generated it as a series of equations that we could just put into Wolfram Alpha. Boop. And here we go. It's working. And if we compare to... Let me actually go back to the calendar. The 906, this number right here, this absurdly long, painful number, is the correct answer. And as you can tell, it would have taken me a very long time to calculate that. Some people on Reddit were doing it by throwing cores at it. Some people were able to get the quick remainder algorithm working, and kudos to them. They're better people than I, for sure. But we just couldn't get it done, and that's okay. That's okay. I hear that today's problem is less insane. We're gonna close out problem 2 because we don't need that anymore. Problem 1's just our new copy because there wasn't that much in problem 2 at the end of the day, so it'll be easy for us to clear that out. So let's get into what is being required of us today. Docking data. As your ferry approaches the seaport, the captain asks for your help again. The computer system that runs this port isn't compatible with the docking program on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the seaport's computer system uses a strange bitmask system in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program can either update the bitmask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. Oh, I'll have to think for a minute about what exactly is the range of a 36-bit integer is. A 1-bit integer would be just like 1 or 0, so which is 2 to the 1, so 2 to the 36 would be the range of an unsigned bit integer. We can look that up in a little bit if it's important. For example, ignoring bitmasks for a moment. Oh, also, if they're doing it as bitmasks, that means that there's going to be 36 items there. Okay. For example, ignoring bitmasks for a moment, a line like mem8 equals 11, mem sub 8 equals 11, would write the value 11 to memory address 8. Okay, that makes sense. The bit mask is always given as a string of 36 bits. Okay, okay. Written in the most significant bit, with the most significant bit representing so the biggest part of it on the left, and the least significant bit, that is 2 to the 0, on the right. Okay, that makes sense. That's kind of how I would expect it to be. The current bit mask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves a bit in the value unchanged. Okay, so it sounds like we might be doing some ors or ands going in here, some bit math. For example, considering the following program: mask equals a whole bunch of x's, 1, some more x's, and then ox. Mem8, so that would be 1, 2, 3, 4, 5, 6, 7, 8. Would that be it? Or no, it's probably 0-based, right, though? So it's either the 1 or the x, depending if they're counting sub-0 to be the thing there. The program starts by, okay, so let's go through the example so that we can understand what they're doing. The program starts by specifying bit mask equals da-da-da, that makes sense. The mask specifies, will overwrite 2 bits in every written value. The 2-bit is overwritten by 0, okay, and the 64 is overwritten by 1, okay, that all makes sense. The program then attempts to write the value 11 to memory address 8. So is mem like a whole bunch of bits, I guess? I don't know exactly what mem is. Is mem like a single value that we're updating repeatedly? Or is that like, is there a whole bunch of different memory locations that we're updating, I guess is. Okay, it does look like they are counting 0. That makes sense. The program then attempts to write the value 11 to memory. So is 11... 11 is decimal. Okay. Okay. Everything makes sense so far, except for the things that don't make sense. And those also make sense in their own way. The program then attempts to write the value 11 to memory address 8. By expanding everything out into individual bits, the mask is applied as follows. The value is, so the initial for 11, 11's turned into binary. That makes sense because this is 1, this is 2. We have 3, no 8, but we do have... So this is 1, 2, 4, 8. Okay, 8, 9, 10, 11. Yeah. So, okay, so mem8 is a discrete location. It's not like the 8th value in that or anything. Okay, that makes sense. Okay, so the result... The bit mask will always turn that into 0. Yeah, okay, this all makes sense. So because the mask, the value 73 is written, because it always turns that into 1. Okay, that makes sense. Then the program tries to write 101 to address 7. Okay, so these are all... Mem is just a whole bunch of discrete values. And memory addresses are also 36-bit unsigned integers. So presumably mem has 36 addressable regions here. This mask has no effect because it already matches. Right. Finally, the program tries to write 0 to the address 8. And it forces the... It doesn't really do anything. It just kind of like forces the bit mask itself to happen, right? '64 is written to address 8 instead, overwriting the value that was there previously. Initialize your Fairy docking program. You need the sum of all values left in memory after the initialization program completes. The entire 36-bit address space begins initialized at the value 0 at every address. In the above example, only 2 values in memory are not 0. 101 at address 7 and 64 at address 8. Right, because they only did that. Okay, that makes sense. Execute the initialization program. What is the sum of all values left in memory after it completes? Okay, so we can get rid of... So let's just peek at our puzzle input to make sure that it matches what... Okay, this all makes sense. Oh, so the mask changes over time. Okay, that's cool. So let's start with this initial mask as our sample input, and just do a little parsing here. I think that basically what we're going to do is we're going to create 2-bit masks. We're going to create a bit mask with all the 1s, and we're going to create a bit mask with all the 0s. And how does that work? No, because it would always have to be both, right? Oh well, we're gonna start off by parsing a bit mask though, for sure. Just out of curiosity, how many memory addresses are there? I wonder. Oh well, we don't actually need to allocate all of them because what we can do is just do hash new, and there's a way to initialize so that any new key automatically starts off as 0 if it's not defined. Hash Ruby. I don't use this all that often, but I think it works out pretty well here, so we don't need to aggressively load up everything from the get-go. Where's the initializer? That's a word. Okay, the block form is what we're looking for. Okay, so it takes key value. Oh, hash and then key. Okay. So every time we access a new key, it'll automatically start at 0 for that. This might not end up living in main, but we're gonna hold on to it for now. So there's 2 different types of things we're gonna need to parse here. We're gonna need to parse masks, and we are going to need to parse memory instructions. So let's just take something, parse input. We're going to take an array of strings for that so that we can put in sample input instead of always running off files. So what are we returning here? Let's think about the structure we want this to end up looking like first. I think we're returning an array, where each array will have mask. I don't know what the mask is going to look like initially. And these actually need to be sequential because they can appear multiple times. So it's going to be the address that we're writing to and the value that we're writing. And actually, this needs to be sequential as well, now that I think about it. So it's just kind of like mask, and then an array of arrays, really. Yeah, this makes sense. Address, value, and the comma is just indicates that we're going to have multiple of these. So how do I want this mask to work? We can initially just copy the string, I guess. Just thinking through how this can work. Because I don't think there's a bitwise operation that just lets you kind of like... It's kind of forces some things but skip others. Well, let me actually think this through a little bit. So if we're just talking about ones and not zeros, this becomes a lot easier. Because if you do like, this is not related to input lines. If you have like 1100, for example, or input forced to have 11 start. And then if we have, and you can force 0 . Okay, so let's suppose input is, let's suppose the mask is 1XO. Let's keep it really simple. Input and input or 100 would set the 1. And then input and 110 would set the 0. Okay, so yeah, so that's how this would work. So let's change this structure a little bit. Add mask or mask. And masks, that's 0. Or mask, that's 1. Okay. Okay, I think we have a good idea of where we're going with this. So let's go through our lines. We'll start off with a result's gonna be like what we end up with at the very end. Let's say current mask set. Let's call that an array as well. Lines each do line. If line starts with mask equals, then starts with. Then we're going to call parse mask. And actually, what we can do each time, regardless, is yeah. What we can do each time is we can always split on the equal because that's common here. Operation value equals line split on the equals. If operation starts with so if we're starting a new mask, we'll throw the result on the current mask set. We'll make a new mask set because we're in a new mask set now, so that makes sense. And actually, I think I do want to adjust this a little bit. Mask set equals end mask or mask assignments. Shrink this down so we have a little more room to work with. And we're just going to say end mask equals mask width. Or mask is mask width. s x 0. Just a shorthand for saying we're substituting these things in this mask. And what else? Assignment equals address we can actually make this a hash, I think. Address value. So that'll be a little easier to read if we make that a hash. Okay, I really like making these into hashes. So the current mask set, that's always going to be this. Current mask set. Block. There we go. Okay, so we're going to have parse mask, and that's going to, we're not implementing that quite yet, but we're going to say and mask and or mask are going to be returned from that. And these aren't going to be strings. These are actually, we're actually going to return an actual integer out this so that we can go a little crazy with this and actually use it for anding and oring, right? Cool. What's next now? This is going to need the value, right? Okay. Else, if operation starts with mem bracket, okay, we're going to be kind of lazy here. Address equals. Oh yeah, we can do a little bit more because we know the structure now. Current mask and mask or mask is or mask, and we can start. We can initialize. And we don't actually need current mask set up here because we actually want the initialization to all happen in the same place. Yeah, this all makes sense. Just say, we'll start that off as nil. And if anything weird happens, I'll probably blow up, but that's fine. Assignment is an array. Assignments, plural. Right. Okay, cool. Gotta keep with our contract. Okay, so we haven't implemented parse mask yet, but it's going to do things here. We have current mask, and that's going to do things here. Actually, we can just stub out a parse mask. We can actually put it under here. Mask. To do implement. Okay, so we're going to be really lazy with this operation. Is there just like a replace I can do on string instead of gsub? Replace. Oh, that's not what I want here at all. That's a very weird function. Why would you even want that ever? That just sounds really weird. Or maybe for a substring thing. Sub. Okay. Okay, so this is basically like the same as G sub, I guess. Yeah. We don't need to globally sub, so I guess sub is fine here though. Sub mem with an empty string, and then sub with an empty string, and then we 2i, and now we have an address. Easy peasy. And then value value we actually always want as an integer, right? No, we don't, because that's sometimes the bit mask. Right, that would have been very bad if I did like that. So let's say current mask set assignments. We're just going to push this array onto it. Address, and then value to I. We're building something here. We're building a little something. It's nice. It's nice. Okay. So the next thing we need to do is we need to actually implement parse mask. This is a reminder of what we're returning. Okay, so I think add mask is going to be mask G sub, and we're just replacing all the X's. These are capital X's, right? Not lowercase. These are all capital. Yep. We're going to replace those all with a 1. And then I think 2i2 does turns it into an actual number that we can work with. So let me just double check that that works the way I think it does. 10 2i 2. Okay, so that would be 2 there. That makes sense. Okay. And so this would be 8 or 4. That'd be 4, and this is going to be 8. Yeah, yeah. So this will convert it from base 2 into a raw integer that we can work with. That will usually present as decimal, but that doesn't really matter. The point is that we have it as a number. And we're going to do something very similar for the OR mask. We're going to replace it with the zeros, and that's how that works. So the order that I actually need that last part. I need the order and mask or mask. It'd probably be better to return that as a hash or something like that, but this is, as I said many times, this is disposable code, so who cares, right? Okay. So let's parse our input, and input lines is where we're grabbing from. And there's a few things we need to clean up here as well. We need to make sure we're returning our result. Let's fold this up just so we can see a little easier. Yep. And before that, we also need to make sure that we're adding the final mask set. Okay, and there's a world where this could be a mask with no assignments, but actually, let's just check the input and see if like that's actually a reasonable thing that can happen. That's not our input. That's from last time. This is where our input is. Let's just zoom to the end of the file. Yeah, okay, so we don't need to worry about any weird cases where it's ending with a mask or anything like that, because that would kind of be a weird state that we wouldn't be handling properly. But it's nice not to have to worry about fringe cases, because we know the exact nature of our input. Otherwise, I would add in some... when we actually process this, I would kind of like... I would add stuff to make sure that if assignments is empty or anything like that. I guess that would ideally like that wouldn't really matter either way. Okay, so it would only be an issue if there were no lines whatsoever, because current mask set would be nil, right? That would be pretty bad. Oh, and I need to not add on the nil mask set. That would be pretty bad. I would have to like special check. Or I guess I don't need to. I can just do a compact at the end, but yeah, that's actually probably nicer. Also, is this result or is it results? Okay, I just had a singular result. Okay. So that way we don't need to check for nils in either case. That's really nice. I feel like I'm missing some things here, but let's just kind of run with this for now. Let's create our sample input file. Sample. Oh, am I in the wrong? I'm in the wrong directory. It's like, why is it not appearing in my file explorer? That's why. Because the file already existed, so I was just updating the timestamp, which doesn't really do anything interesting at all. So we have, we're going to be parsing the sample file. We do have that lined up. Let's just pretty print what we're making and see if like the structure matches what we expect it to, just to make sure we didn't do anything really dumb here. We did some dumb things here. I did starts with instead of start with. Okay, that's... I often forget whether or not method names are pluralized or not. Undefined method bracket for nil class. Okay, so this is on 64, I think is just the end of our program. Then we go to 5, and then 18. That's just in our loop. $33 is where the real issue is. Okay, this is very odd, because current mask set should be getting assigned, because we're hitting a mask first. So let's add a binding pry and just see where this is going sideways. It's probably something very simple here. Operation. Oh, I'm checking for the equals when we split that off. So We wrote the start with line before we did the split, so that's why it's bad. Okay. Like I said, really dumb errors happen all the time. Oh, I didn't consider this was going to be... does Windows have a binary calculator that I can look at in programmer mode? Okay. Because I just want to see if the bit mask... What? Invalid input? Oh, I guess that is invalid input. I copied the whole thing, didn't I? I didn't just copy the number. I was about to be aghast. Okay, that looks correct. Okay, so we want just the 0. And so that looks correct. So we see in binary that matches what the bit field should look like there. Okay, and the OR mask is just 64. No, I want 64 in decimal. So in binary, it sets the 1 bit. We have 0, 1, 2, 4, 5, 6. That looks correct to me. Besides that, we want to... These numbers are in decimal, so we expect 11. Are these in decimal? Yeah, these are decimal. So we expect 11, we expect 8. Yeah, yeah, okay. And these are just assignments. Okay, so let's start processing these lines. Okay, so we already have our memory hash here that's initialized at 0. So let's run with that and stay in this main function for now. It might end up feeling like a little complicated, so we want to break out, but we'll just start off in here. I'm also, I kind of... Part of me wonders if I want to break that up, but I think that's okay. I think that's okay. So we expect this to be an array of mask sets. Perfect. Okay. The current AND mask is going to be AND mask, OR mask is going to be OR mask. So far, everything is going by plan. So let's do each assignment in task set assignments. Each do assignment. Or actually, I guess each element of this array is going to be an array, so we can break this out automatically for us. Or did we... Oh, we did turn it into a hash. Okay. We can't break it up immediately in the array. That's fine. That makes it just a little easier to read. Okay, so we don't really care about the old value at any point, right? I don't even know if we care about this initialization, right? Just by specifying mask, the mask gets specified will overwrite 2 bits. The program then attempts to write the value at the address by expanding everything into bits. The mask supply as follows. Okay. So we're just doing plain assignment. So the fact that it starts off at 0 doesn't really matter. What is the sum of all values left in memory after it completes? All the values are going to be 0, so that doesn't matter. That we can just ignore the zeros. The zeros are dumb. The zeros are cringe. We don't need those in our life, so we can just do this instead. We can just have a normal hash. And just, because we're just blindly writing to it, right? So value, let me see, Ruby bitwise operators. I think it's just like single AND and single OR, but yeah, that's what I thought. Perfect. Perfect. So we're just going to do assignment value and mask or mask. That should be fine, I think. Am I missing a parens? I'm missing a parens. Once I have my parens, that should be fine, I think. And then we just have mem assignment address. We can actually make this a little easier to read, I think. Value equals assignment value. Address equals assignment address. We're working with the value first, so we're going to put that closer to the things that are editing it. So we can do and equal and mask value or equal or mask. Great. So mem address equals value. Let's actually just put this closer to that so that similar things are grouped together. Makes it a little easier to read. This is all very simple so far. We've been taking a little time with it, but it's not none of this is hard. This is just basic road stuff. Okay. They might spike things for part 2. Like yesterday, it was very trivial for part 1, and then it required math I never heard of before in my life for part 2. So easing into this one is what we're doing. So now that we've done all of that, let's pre-print the mem and see what we have, because it should match kind of like the transformations that were happening in the problem. Okay, we did something wrong. No implicit conversion of symbol to integer. Well, that's not what we want to see at all. 13. Assignment value. Didn't we do? We did end up doing. Okay. This is a lie. This is a lie. We said damn readability. Damn readability to all heck. That's fine. This actually makes this part a little simpler because we don't need to do that, and we don't need to do that anymore. Okay, so what is... In the above example, only two values in memory are not 0. 101 at address 7, and look at what we got there. And then 64 at address 8. So we're doing really well so far. Let's change this up and use our real input. Let me just save that locally. Put that into our project. And run that, and I think we should be good for part 1. Oh, there's one step we still have to do. So before we do that, let's we have to sum up all the values left in memory after complete. And we're still on our first version, right? Nope. Input. Let's stay on input sample. Just to be on the safe side and confirm that we know what we're doing. 165. Okay, so we did know what we're doing. That matches 165 over here. All we did was sum up all the values in our hash table, because the exact memory address does not really matter. Okay, and let's run it for our input. And for our input, it's saying 0. That seems suspicious to me. So let's print out some additional things. First of all, do we have... That's not correct. That's not the correct input. We have fraudulent input happening here. Maybe I clicked I did not want to replace it, but I'm pretty sure I did. What is happening? This is very bizarre. What is going on here? Delete this. And then save this. Okay, this is what? This is very bizarre. I don't know where this is saving. Well, that's very confusing. This is not a part of the journey that I was expecting an issue with. I guess what we can do is this. But I'll definitely want to figure out what's going on for next time. My Chrome is just saying that the file is removed every time I save it, so I don't know if like some weird caching thing is happening. Okay, that's a much bigger number. I'm just going to go ahead and trust that this number is correct. And if not, we'll clean it up. Okay, so that number is correct. Okay, so now we're on to part 2. For some reason, the Seaport's computer system still can't communicate with the ferry's docking program. It must be using version 2 of the decoder chip. The version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. If the bitmask bit is 0, the corresponding memory address bit is unchanged. If the bitmask bit is 1, the corresponding memory bit is overwritten with a 1. If the bitmask is X, the corresponding memory address bit is floating. Floating bit is not connected to anything and instead fluctuates unpredictably. What? In practice, this means the floating bits will take on all possible values, potentially causing many memory addresses to be written all at once. That's very odd. That's very odd. For example, considering the following program. Max 00x1001x, and then we assign memory of 100, and then we pick this other bit mask, and then we assign to 26 1. When the program goes to write to memory address 42, it first applies the bit mask. So initially it's how does this bit mask compare? Okay. X101. After applying the mask, 4 bits are overwritten, 3 of which are different and 2 of which are floating. Floating bits take on every possible combination of values. With 2 floating bits, 4 actual memory addresses are written. So are they all written to the same place? That's very odd. Next, the program is about to... So it has those 2 x's, so it writes every possibility for those x's. Next, the program is about to write the memory address 6 with a different bit mask. This results in an address with 3 floating bits, which causes it to write to 8 memory. So that makes sense, because there's 2 different possibilities, so it's going to be the number of things that are going to, the number of possibilities that are going to increase are going to be by 2 to the number of x's. Okay. So it's 000, 100, 0100, okay, and it just goes on and so forth. The entire 32-bit address space still begins initialized at the value 0 at every address and still needs to sum of all values left in memory at the end of the program. In this example, the sum is 208. Execute the initialization program using the emulator for version 2 decoder chip. What is the sum of all values left in memory after it completes? So, the part I'm still struggling with is, does it... I need to reread this because I don't think I fully understood that. Okay, for some reason the Seaport's computer system can't communicate with your ferry's docking program. It must be using version 2 of the decoder chip. A version 2 decoder chip doesn't modify the values being written at all. Okay, so it changes the memory addresses. Okay, that makes a whole lot more sense. So if there's x's, we spew to tons of different memory places. Okay, so this is going to be a significantly different implementation than problem 1. Let's make a copy. still very confused why it didn't let me download the input. I'm wondering if Chrome doesn't have access to right to my desktop for some reason. Because I just did a Windows update and it updated like a million different things. So that's possible. Okay, so we're going to change the structure for sure of what a mask set looks like. So the idea of so parse mask is going to need to be different. I kind of hate my entire structure now. I wish I knew this was where this was going. This is just like a significantly different problem altogether. I guess what we can do is we can change this to just be like a pure parsing thing and then figure out what we do from there, rather than trying to do any processing during the parsing. Because I kind of have some processing, I'm turning the mask into stuff. Okay, so let's say that let's make this just an array. Mask set's just gonna be an array instead of a hash. Result equals current mask set. That's valid. We don't really need parse mask now because we're just gonna have the literal mask there. Or do we? I guess we let's back up a little bit. So maybe we just change this to and masks or masks. Because we need and masks, we need multiple of these. Ugh. Mask to end with address. Mask to or with address. Let's make another. So a lot of this work's going to happen in parse mask. I think parse mask is going to become less trivial. So let's make the suppose mask is we ultimately need if input is we need to zero out every x and we need to one every x. We need to like have every single combination of this. For or masks, we just we have zeros added in to ignore stuff. If mask is 0, the old behavior of X has moved to 0. One is changed to 1, so and masks or masks. Or masks. So how do we force things to change to 1 if it 1, but not touch it if it's 0? Let me think here. I can force 0 to change to a 1 by ORing it with 1. And I can force a value that's 1 to... okay, so... the way I do this... So the no change one actually needs to behave a little differently. This is actually kind of like a complicated to think through. What are the masks I need here? So, like, let's say that the mask was just X. Obviously, just ending with turning the... We want... This might actually be a lot easier to turn to string and not use bitwise, actually. That sounds so lame, though. Let's play around with like a little implementation that does that and see where that lands. So just to double check, I can call 8 2s2 to end up with a bitwise string. Mask split with x 2 mask bit dx. Value binary. Value b2. Okay. Actually, I don't need to do a split. I don't know why I keep on thinking I need to do a split. Oh, I need to do it with each though. Yeah. Yeah. So I need to do it up there. I don't need to do it down here. Value bid. Right now our masks have values of 0, 1, x. I think what I want to do is I want to expand out the masks with like kind of like different values. So we can have like in the case of like there's two variables, we can explode it out to make all the possible masks that we can. And there's just like there's more than two states to keep track of, and that's why this is really hard. Because you have the state of do not change, force 1, and force 0. While before we had force 0, force 1, and do not change. Oh. Maybe I got confused because they changed the how ones and zeros work. I think first thing I'm going to do is I'm going to turn masks into kind of like their original format, where X does something weird. So let's make that Y now. We're going to turn... And ones still behave exactly the same as they always have. So that makes sense. Huh. And then we're just gonna do like shenanigans with the Ys. Yeah, I think this is good. This is good. So just to recap, what we're doing here is we have a bit field that has values of 0, 1, and x. And the way that 1 works is that 1 will always turn a bit into 1. A 0 will always leave it unchanged. And x can be a 1 or a 0 in every combination. How do I want that explosion to happen? That's actually the part that's kind of weird to get my head around. Is there a way to get indexes of... I want to get all the indexes of something. I mean, that's easy enough to implement on my own. Start menu is bothering me. I want the start menu to go away. There we go. Okay. What was I saying there? Right, Right, so we're at the explosion. So, and I want to find all the indexes where y is now, because y is like the new thing. We're going to convert these into old format, but we're going to make a whole bunch of them. So if we do mask, map, and all with index, I think that might get us what we want. We're going to need to split that for innumerable things to work in. I think I actually need to do a map with a reduced, I think. A map with a... Because find all is going to just return the actual y's, not the indexes of them. Okay, so map with index, bit, index, y indexes. Get rid of that. We're gonna do mask. If bit equals y. IDX. Do this as postfix notation to make it a little more compact. And then so if the if does not evaluate, the whole expression is going to be nil. So we're going to have either the index that we're looking for or nil, and then we're filtering out all the nils with compact. What happens now? Is this like a scalar multiplication at this point, I guess? Here. Linux is each. I want something like 3, 4, 5 turn into a truth table. I basically want to generate a truth table. Okay, so I don't really care about parsing. Car's empty. Okay, actually, I don't know what alpha is, but I'm assuming kind of like a word character thing. \W equivalent. I mean, essentially what I need to do is I need to like if I have the number 2, I want to be able to generate if I have the number 1, I want to generate like 1 0. If I have 2, I want to be able to generate like 0 0 0 1 1 0 1 1. I don't know why my brain's struggling with this. And so that alone would kind of look like that array and times the inner loop would be n times because we have 3 0 0 1 0 1. Oh, I won't. I won't try. Don't worry. I'm thinking through what like the generic form of this would be. Combinations. Kind of generically what I'm looking. I've never repeated permutation come from. In the standard library? Okay. When invoked with a block, yield all repeated permutations of length n of the elements in the array. Then return the array itself. That's interesting. So what if we do one, actually, this looks like, oh, that's cool. It does syntax highlighting like that. I didn't know that it did that. Well, that output was not very useful. I guess maybe a 3 permutation would be. Zero. Okay, yeah. Okay, this is exactly what I'm looking for here, I think. So how do we apply this to what we're doing? So we know that the repeated permutation. Let's just, after we have, okay, so we have our y-indexes. Size. Perm. If I do map on this, that'll give me 8 things, which I do want. So all I need to do is, I know the indexes where I want to replace. Make sure that. Okay, so strings are mutable. I don't have the shebang line on top that makes them immutable. Okay. So we can do map on this. New mask. I think we can do clone or something instead, but this forces to make a new memory, which is what I want. So let's do perm. Each with index. Bit. IDX. Now if we look at y-indexes, IDX, that's going to correspond. So we're going to take new mask. We're going to replace the y with the bit. Does this work with strings? Let me just change. I hate the start menu. 0, 1. Because we're actually dealing with the strings here, I think. Okay, it works just as well with the strings. Okay, we're chilling. We're chilling. So perfect. Oh God, it took us so long to get to this point. But I think this does exactly what we wanted to do. And then we have new mask. God, this is actually really nice. I really like this. So, because we're doing map, repeated permutations, results in, like, let's say we have a 3 y's in our thing. Okay, so what we can do is we can get rid of all this. And I'm going to open up my, I think I want my old parse mask again. Let's get into here. I want my old parse mask back. We're going to name it something different. Turn mask into Endor. Because we still have like the X bit in there. We turned our zeros into X's because that's what we need to do. For our mask, we turn X's into. So let me think through this and make sure the behavior is the same. It is. It most certainly is. It most certainly is. So that's the behavior we want. So for parse mask, I think what we do is we explode mask the mask. So this is going to give us a whole bunch of masks off of this. Exploded. And then we're going to turn mask into and at this point they're already integers, so we don't need to do anything more to them. Returns mask set, and for this we're going to say that mask set is and or. Okay. Whew. Okay, okay. Let's get back into our earlier thing. So now we can get back to where we can go back to before. Parse input. This is where we want to be. Is this still relevant framing? Ooh, I didn't want to do that. I need to unbind my my Vim for Control F. parse input. Okay, so the returns are going to be a bit different now. Or does it need to be? I don't know. Masks. Masks, what do you return? You return something else. And or. Shrink that down. And this. Matching the data type seems to be kind of complicated at this point. Might be a point where OO makes sense. I don't really want to make that jump, but it's not like unreasonable at this point, I think. That seems reasonable. The assignment part stays the same. This all seems pretty reasonable. So let's back out. So we take parsed, and now we need to loop through the masks in mask set. Mask set masks each do. Add mask. We could actually do a quick test to make sure that what we're parsing looks reasonable. Ooh. Sample. About that. Okay, we did bad things, and we're being punished for it. 46. Oh, we didn't include a comma here, so that's pretty easy to fix. I gotta get through this soon because I haven't eaten dinner yet. And I'm starting to get hungry. Unexpected end of input. Let's collapse things down until makes sense. probably just missed an end somewhere. Well, we can just comment things out until we don't get that anymore, right? Okay, so it's not an issue in parse mask. We didn't think it was. I don't think it's here either. Test that as well. Test load mask. This might be it. Chilling here. In here. Oop. Okay, let's see what this. Nope. Why would be in here, but it is. Who knows? Okay, we have something different now. 26. Okay, I accidentally undid this change. That's taking a long time to do, isn't it? It's taking a very long time to do. Do we have our sample input still? Input sample. Look at what that looks like. Oh, that has a lot of X's in it. That's an unfortunate number of X's. Let's make a sample 2. I think that they have more sample for us here. Okay, so we're in part 1. Where's part 2? So here's an example for part 2. That crap to kind of just think through. Need problem 1. Okay. So looking at our sample 2, does this make sense? Let's open up our calculator again and compare. From binary. So binary, when we're ANDing, we want to persist all of this stuff. This stuff, we want to persist everything that's not an x. And then the x's are variable. So for the first one, we're zeroing out. Let's just look at the ands initially. Okay, now it's just 1. Oop, that's not what we want. Okay, so because there's only 2, and I kind of see how this is going, that looks normal to me. That looks good. Now for the OR, for the first case, we're persisting both. And then we're persisting only the first one. We're persisting the ones always, but we're only persisting the first x. That kind of makes sense. Let's just look at this versus the first 2 here. So in this, it looks like we're dealing with the case of 0, 0. So in that case, what would the OR look like here? The OR would be 0 here and 0 here, I think. Oop. Yeah, I think that's where we ended up. The important thing for the OR is that it's zeroing out the things that need to be zeroed out. Yeah, I think this is accurate. I think this is accurate. So let's run it with the rest and see if it makes a reasonable reasonable play here. Actually, why is this so big? Oh, right, because we want to persist. We want to persist that one. So that all needs to be ANDed. We don't really care if this is 1 or 0. Because this is actually the equivalent of in our old version. It starts with bang inside. No, terrible. The zeros are going to be x's. Or no, let's make the x's y's real quick. X into y. And fine. Why is my insert key not working in Notepad? That's very unfortunate. And these should all be X's. And that would make these oop, 0, 0, 4, 1, 0, 4. In this direction. Or 1, 1. So those are like the 4 that we're looking to get out of there. And then we split them into ands and ors. So then it gets more complicated. Okay. This is just like really complicated to just have a mental model of everything. That's like the part that's actually tricky. So let's finish up the rest of the program given these constraints. We have our parsed. For each mask, we have an AND mask and an OR mask. Don't need those lines. We're not messing with the value this time. We're messing with the address because that's what the problem says for this one. Let's So maybe we want the I think we want the assignments to be the outer loop. Because I think that's like the order we want everything to happen. Transformed address. Address. And mask. Or mask. Because we don't want to mutate the actual address here. Because we need that for the next iteration of this. So, address value. And we end, and we end, and we end. So that part of the structure can stay the same. We end some more. And let's see what mem looks like at this. Oop. We don't need this. No, we exited out early, so we don't need that now. Go. So given these, given this example, which are overwritten, 3 of which are different. So what's the end result here? Did we do it? We did not do it. Because we were supposed to write to 4 different, we're supposed to write to 8 different memory addresses. Let's add a binding pry here and just see what transformed address looks like each time. We have 26. So we did the first one right. Oh wait, am I looking at like 2 different examples here? What's my input sample? Where did I pull this from? No, I input sample 2. Okay. So 42. Oh, 42. Mask. Gold. I think let's take a possible combination. Oh, I didn't do it on the transformed address. That's my issue here. Maybe this just works now. That's a very easy mistake to make. Okay, so let's run this. Only better this time. Wrong. On line 7. What did I do? Did I delete the wrong thing? Yeah, I deleted the wrong thing. There we go. Okay, I don't think that we did it. Oh wait, I undid the fix also. Okay. 26, 27, 58, 59. Now the question is, did I apply the masks correctly? Two, three, four. I don't know if we did this correctly. Doesn't look like we did this correctly. see what the sum is here. I don't think that adds up. No, I'm almost certain it doesn't. Oh, it's correct. We added it up. We did it. Okay, let's just try this. I'm kind of tired. I want to eat my dinner really bad. So I'm just gonna switch over to input, our main input for this problem, and we're gonna see what happens here. See if we have shame or success. Uh, hmm. Falling out printing. That's not great. But that's after we did all the processing, so that's very odd. So we're just gonna blindly put this in and hope for the best. And we're correct! Sometimes it's nice to be lucky. Okay, I'm gonna throw all this onto GitHub. Thank you so much for hanging out. This has been 2 hours and 20 minutes of bliss to share with all of you, and I'm very glad you could be here for it. But I'm done. I need to eat. I need to not be coding for a while. Coming off a day of work and then going right into this, it's a lot. So I think this is goodbye for now until tomorrow, and then we'll come back and we'll write some more code, and it'll be great. Everything added here. I hope you guys all have a fantastic day, and thank you for coming out. Thank you for hanging out. If you have your own suggestions, throw me a Twitter, throw me a Discord. Let me see what you got. Show me your GitHubs, and we can talk about it and see who came up with the cool solution. Until next time.